A warm welcome to the Digital WE Days. It's already Thursday afternoon in Germany and it's raining right now, but nevertheless we have a great presentation to offer you. My name is Doreen Schäfer and I will moderate this session. Next to me is my colleague Andreas Nadle.
Hi, Doreen.
He's a field application engineer for our company. Today's meeting will be about design, layout and simulation of three-phase AC/DC filters. Designing EMC filters requires precision, from simulation to lab testing. But how do you dimension a filter based on real EMC signatures? Let's walk through the process. The stage is yours.
Thank you, Doreen. Good afternoon, everybody. Well, in this session, you will learn what's the source of interference, what kind of components you will need for a filter, how to calculate and simulate this filter. The simulation we will do with the free software LT-Spice. We will show you how to design a filter from a schematic and layout point of view, because there are some very important topics. And of course, at the last but not least, we will compare the calculated, simulated and designed filter in real measurements with a real device under test. You will find a related app note. It's not released yet, but if you need the PDF, I will send it to you in English or in German. Just write us an email and you will receive it. Well, the sources of interference, there are main interference source in three-phase applications like ours and many other applications. We have a differential mode, which is the current is only traveling between plus and minus, or L and neutral, or L1, L2 between the phases. And the common mode is the current between the phases, and the return path is the earth. The differential mode currents are easy to follow because they are traveling the same way like in the schematic, and usually we have pretty large currents in the range of milliamps or amps, and we can easily filter them with pi topologies, T or LC filters between the phases. Whereas the common mode currents are more tricky to follow because they're always running unexpected paths which are not drawn in your schematic. That means you can only filter them with shielding, with Y caps against protective earth, or with common mode chokes, or you decrease your du to dt. That means these currents are usually pretty small. We are talking of in the microamp range, but these are usually the biggest challenge for EMC designers. Here we'll see a typical application. Let's say a three-phase PFC, totem pole PFC with a DC link, an inverter, and an AC motor with three phases. And you will see here the differential mode current path between the phases. This we can fight with the stray inductance of the common mode choke and the X capacitors. And to fight the common mode currents, we will use the Y capacitors and the main inductance of the common mode choke. Usually you measure against a three-phase listen. This is how it looks internally. Important to know is that you measure against 50 ohm resistors. And in differential mode, two of them are in a row between the lines. So in differential mode, we have 100 ohm of impedance. This is important later on for the LT-Spice simulation. And in common mode, we have all of them in parallel, which results in 16.6 ohm of common mode impedance on the listen side. This is the line impedance stabilization network. And this is an impedance which is already known for simulation. What kind of filter components do we need? Of course, we need Y capacitors to filter the common mode against protective earth. You can use film capacitors if you need bigger capacitance. The drawback is the ESL of these components is higher and the high frequency behavior is not that good. But you can choose a wider pitch for bigger creepage and clearance. You can also choose MLCCs with a Y2 rating. The advantage of this is they have very low ESL, and so they are very good in suppressing high frequency content. So over 5 to 10 megahertz, they are performing better than the bigger one. The drawback is they are limited in capacitance, and the creepage and clearance can, in some cases, not big enough. You can choose Red Expert to select our components just for information. There you will easily find the required components. You can filter for capacitance, for creepage clearance in regard of component size. So this makes your life much more easy. For X2 capacitors, we also have some components which maybe can help you. We have the FTXX, FTX2. These are rated for 310 volts or 275 volt AC. And we have the more robust FTXH. So they are very good suited for high humidity and high temperature applications, like in server applications and so on. So, but usually for the, let's say, most industrial customers, the standard FTXX is good enough. So we place them between the lines, but in a star connection you will see, because usually for 400 volt applications you need an X1 capacitor. The drawback is the X1 is much more bigger and more expensive, but it can handle 5 kV of surge, whereas X2 capacitor can handle only 2.5 kV surge. But as you put them in series and form a star connection, you also have the same advantage in surge capability. Combo chokes for 500 volts, we have the manganese zinc ones. And this is they are working pretty good in the frequency range below, let's say 5 megahertz. So there is the advantage of manganese zinc. And for the higher voltage applications like 760 volts, we have also manganese zinc and nickel zinc, nanocrystalline, sorry. So the nanocrystalline has the advantage of a wider frequency range, which is working pretty good, whereas the manganese zinc, as I told you, are better in the lower frequency range. And of course, to increase the surge capability of the system, we also provide you with the required varistors for your system, and we can help you there to calculate them. All right, let's go to the filter structure. That's the most important point to understand. From a common mode point of view, we know the listen impedance is 16.6 ohm on the left side, and the noise source impedance is your system. And usually, if it's not known by your own, you can put there a range between 1 kilo ohm and 10 kilo ohm. This is important then for the simulation. So on the right side, you have a very high impedance source. On the left side, you have a low impedance, sink. And therefore, the Y capacitors must be placed first directly beside the noise source, whereas the common mode choke is placed after the Y capacitors in direction to the listen. And this is the protective earth, and we are here with the 1, 2, 3 lines. From a differential mode point of view, this is different, where we have the 100 ohm impedance of the listen, because 250 ohm resistors are in a row. And the noise source is usually the input capacitors of our, let's say, main stage. And there we can assume a much more lower impedance, usually between 1 ohm and 10 ohm, usually in high voltage applications. That means we place at first glance the leakage inductance of the combo choke on the right side, directly beside the noise source, because it's making always the opposite. We're placing a high impedance filter component beside a low impedance noise source. And the X capacitors are sitting in parallel to the listen impedance of 100 ohm, because they're providing a low impedance path. So this is important to understand the structure. Our setup, to test our designed and calculated filter, we have a 400 volt application with an EMC filter, with an inverter and a 4 kilowatt industrial fan. In the lab, it looks like this. And this is our EMC signature with absolutely no filter components. And this is what I really recommend for you. At first, make a measurement without any filter components included, because then you really know how much attenuation you will need, and then you can calculate in the end your resulting filter, and it will not be too big and not be too small after all. So that's the best way of doing this. And the interesting frequency span is from 150 kilohertz to 30 megahertz. And for us to calculate the filter, we will take the lowest frequency with the highest amplitude, because this gives us the, let's say, lowest filter corner frequency, and this results in the biggest component. And we can see at a roughly 200 kilohertz, we need at least to fulfill the, let's say, limit class B of CISPR 16, for example, and we need there 65 dB microvolt of damping, 60 dB of damping to stay under the limit with a sufficient margin. So this is our starting point, 60 dB of damping at 200 kilohertz. Also important to understand is the common mode current loop because of the whole setup inside the chamber. Now we can see, we know already the impedance of the listen against the EMC chamber. We have the wiring and we have the inverter, and the inverter is inside the motor chassis. And the motor chassis and inverter and the motor windings against the motor chassis provides us, we measured this with an LCR meter, coupling path. This is a stray capacitance from especially the windings against the chassis of around 870 picofarad, which results in roughly 200 ohm of common mode impedance inside the motor and the motor against the EMC chamber. We know the distance, and therefore we know the, let's say, the size of the chamber and the size of the device under test. It's roughly 1 meter square, and therefore we can calculate with the epsilon r of air the inductance or the capacitance of this distance, and this ends roughly in 7.2 kilo ohm. This is something then we can put into the LT SPICE simulation to get a better feeling if the resulting insertion loss is high enough or not. In front of, we can measure what is dominating, common mode or differential mode, to get a clue if we have to, let's say, select rather bigger X caps or bigger common mode choke to see what kind of interference is disturbing us. And with this measurement, we can see below 50 kilohertz, the differential mode is dominating, and over 50 kilohertz, common mode is dominating. But they are pretty close together, so we make it a little bit more easy for us, and we assume for common mode and differential mode, we need both 60 dB damping at 200 kilohertz. So this is the resulting filter impedance curve we will need to fulfill the requirements. We start with 60 dB at 200 kilohertz, and then we need less and less, let's say, filter insertion loss, because the interference is also going a little bit down and the limits are going up. All right, let's start with the math. Important to understand is the structure, what we build up here. I decide to build up a pi filter from a differential point of view. That means the stray inductance and the two X capacitor stages, building a pi structure with 60 dB per decade of filter insertion loss after the corner frequency. And the common mode is the main inductance of the choke and the Y capacitors. And now I split up the Y capacitors a little bit. I use two bigger ones, in total roughly 100 nanofarads, to filter the low frequency common mode current. And they are connected to the star connection of the X capacitors. This helps us because then the leakage current is much more smaller as when we connect them directly to the phases. So this is then an advantage when using a star connection of X2 capacitors. With in theory, the current there, the leakage current is 0, but in practice we have some, let's say, tolerance of the caps and some tolerance of the voltage between the phases. Therefore, we have not ideal 0 leakage current here, but it's much more smaller. But we can use the smaller RF MLCC caps directly connected to the phases between to the protected earth. So we can use let's say the beneficial high frequency behavior of the small MLCCs, and as they are below 4.7 nanofarad, they do not have a high leakage current. So we can combine both, let's say, good properties of the MLCCs and the film caps. And as we have just a filter structure of 40 dB per decade, we need, let's say, a lower corner frequency compared to the differential mode filter. So the effective CX, we have there are two connected in a row between the phases. So only the half of the capacitance is working. And the Y capacitor in the row with the X capacitor is dominating the overall capacitance there. So the formula you see below. Okay, next step, I need to know the formula how to get the right corner frequency. In our case, we know we have a switching frequency or a frequency of interest of 200 kilohertz we put in here, and we need a required damping of around 60 dB. And this is then the required corner frequency for the common mode filter, because in the common mode we just have a two-stage LC filter with 40 dB per decade. If we, for example, would have two LC stages, which we do not have in this structure, you will get 80 dB per decade, which gives us a much more higher corner frequency and smaller components if needed. And the differential mode stage in our case is a CLC. So we have two X stages and the leakage inductance here. So we have 60 dB per decade, and we need 60 dB of damping, and also at 200 kilohertz. Additionally, we do have to do some math, because in a pi structure, these two capacitors from an RF point of view sitting in series. So we just have the half of the capacitance effectively to calculate our corner frequency. All right, now put this all together. The damping, we need a 60 dB at 200 kilohertz for both differential mode and common mode. So that means we start with the common mode and the differential mode. That means for both, after we put all in the formulas, we need for the common mode a corner frequency of 6 kilohertz around, and for the differential mode we need around roughly 20 kilohertz, because we have a pi structure here, and here we only have a LC structure. Therefore, the components will result in bigger, let's say, values after all. Okay, we have to start with something. Therefore, we have already defined the Y-caps because they are safety relevant. We cannot put in too big Y-caps due to the leakage current. So therefore, we just calculate with the bigger Y-caps, because the smaller ones plays no big role here, but you can also, of course, put them together. So effectively, I have used two 47 nanofarad as film capacitors. And effectively, and they are connected with the X capacitors, we are resulting in 94 nanofarads of Y capacitance. After that, we can calculate the main inductance for the common mode. We know the corner frequency, we know the Y capacitors, and we can rearrange Thomson's equations. And therefore, we get, from a mathematical point of view, 6.8 millihenry of required minimum inductance. But the components, especially combo chokes, suffer a lot of, let's say, tolerance in practice. Plus minus 30% is not uncommon. Therefore, we give us more headroom, and we choose off-the-shelf component with 8.4 millihenry. This gives us theoretically a new corner frequency if the component really have exactly this value of around 4.7 kilohertz and theoretically 62 dB of damping, so a little bit more headroom, which is wanted. Next step, we define the leakage inductance of the common mode choke. There we can either measure this with an LCR meter, or we go to our Red Expert software to the differential mode impedance curve. We are taking a frequency where the impedance curve is linear, and then we read the XL. The XL at 100 kilohertz in the curve is around 40 ohm. And therefore, we can calculate the stray inductance or leakage inductance of around 62 microhenry. And the last step is now to calculate the required X capacitance. We know the corner frequency of 20 kilohertz. We know the leakage. Therefore, we can calculate the, in the end, needed X capacitor between one line. It's around 1 microfarad. But we must choose here a 4 times bigger capacitor, because we have to divide it 2 times by 2, because we are connecting them in a star connection, and we have them in the pi structure also in series. So therefore, the end result is 1.18 microfarad, and this gives us then the damping of roughly 4.62 dB. All right. Just one hint for you, nanocrystalline cores, you have to be careful, because in the data sheet, for example, we take one of our parts, but this is, let's say, true for every manufacturer. This part's suffering some frequency-dependent permeability. You see the lower part of the curve is steeper, and then it's getting flatter. That means everyone is measuring the combo choke or the inductance, the main inductance at 10 kilohertz. At 10 kilohertz, we can really measure roughly around 18 or 17 millihenry. But if you go higher in frequency and the curve is flattened, we see this is our frequency of interest in the EMC, 100 or 200 kilohertz. We are in this range. And in this range, we do not have the datasheet value. We have a lower impedance here and the lower inductance after all. So then you have to really calculate with this value, and this is something you get also out of Red Expert, for example, just to be aware of it. Manganese zinc, do not until you stay under the resonance frequency, do not suffer this. All right, how can we simulate this with LT-Spice? You can find our models already included in a contrib file of the standard LT-Spice simulation installation. So they're already included in the contrib file. And the upper one is the differential mode the simulation with 100 ohm of listen impedance. I put also in the capacitance of the varistor between one phase pair. I have the X capacitors here, and we only measure here then, or simulate here the stray inductance. And then the input impedance, we make a roughly estimation of around 1 ohm, and we're using a voltage source, a low impedance one. And for the common mode, we have the 16.6 listen impedance plus the impedance from the motor chassis to the EMC chamber, plus the let's say the impedance from the motor windings to the motor chassis. And we are using not a voltage source, but a high impedance AC source, because common mode is suffer a high impedance source, as I already told you. And we put here in the Y capacitors against ground. Ground is in this case protective earth. And you have to shunt the three, let's say, lines on the common mode choke together to get the main inductance against the protective earth. And after all, it looks like this. We have to stay with the insertion loss above the black line, because the black line is that what we need at minimum to fulfill all the requirements. And what we calculated was around 60 dB, and we also get this in our simulation pretty good. And as we can see, the common mode insertion loss and the differential mode insertion loss stays always nearly above our limit. So this filter would be a great choice to start with the first prototype. The PCB, so the schematic for the PCB looks like this. I have done it in Altium. This is already known from the schematic before. I added here the required varistors. I also added here some metal bolts to connect or to provide a really low impedance connection, because this is critical that our Y capacitors are really working as expected. And the layout looks like this. We have our device under test on the right side and the grid on the left side. We can see here the X capacitors, the big one, and here the bigger two Y capacitors. And they are connected directly each other, or everyone gets its own bolt to the housing or to the, let's say, to the chassis plane or to the reference plane. And this is important, not to connect them on the same PCB over a long microstrip, otherwise you will compromise the filter. And on the bottom side, you can see the smaller MLCCs. They are also connected on the lowest impedance path possible to the protective earth. Only if you connect them like this, you can really expect the best performance of the part like you simulate them. If you connect them via a long, let's say, polygon or a long microstrip, and connect them all together on the same PCB and go then on another corner to the protective earth, you will lose a lot of insertion loss. All right, last but not least, let's measure and see what's the result of our filter. So this was the let's say, the beginning without any filter components. And now this is the result with our filter. So this is everything together, common mode plus differential mode, quasi-peak. So this is what you have, what you really measure in EMC. And what we can see perfectly, we get our required damping, exactly what we calculated, and we stay over the whole frequency range from 150 kilohertz to 30 megahertz under the limit. Of course, in some areas we are maybe a little bit close, but this can be optimized then in let's say, optimizing the filter components. But for a first draft, it was pretty good fitting, let's say. And what happens if you place the Y capacitors on the wrong side? Because I had also many customers in the past which are connecting the Y capacitors, not on the device under test side, but on the grid side of the common mode choke. So from our perspective, that means they are connected them on this side and not on the device under test side. The result is pretty surprising. The insertion loss is pretty poor, to be honest. To see the orange one, we just placed the Y capacitor. So I just turned the filter 180 degrees because the filter is symmetrical, but only the Y capacitors are not symmetrical there. And if you place them on the wrong side, you will lose nearly 50 dB in the lower frequency range, and even in the higher frequencies range, you see the deviation is much more bigger. So this is a good learning, I think, for many people to really place them on the right side, because they are providing a capacitive divider from the noise source impedance back to the source of interference. All right, and that's all from my side. Thank you very much for your time, and I'm open for your questions.
So, thank you very much, Andreas, for your compelling presentation.
Welcome.
So, first of all, before we start with the questions, I'm going to share the handout to your presentation, so all of you should be able to see it now, and you can download it. So, I also saw that many of them were very active in the chat. So, let's have a look at the questions, starting by the first one. This came in from Herbert. He was asking, are your components available in the LT-SPICE standard library?
Yes. So if you place a capacitor from a standard library or an inductor, you can go to pick a new inductor or pick a new capacitor and just copy-paste our article number there, and you press find. Then you will find, usually if you have the newest update, all components in the standard library. And the common mode choke and transformers, everything which is not a standard component, you have to go to the contrib folder if you place a new component. In the contrib folder, you will find the common mode chokes, and then you open the model, you make a double click in the middle row, and then you find a drop-down menu, and then you can select inside the common mode series the appropriate part.
I hope everyone could follow his instructions. If not, you can have a look at the recording afterwards.
Yeah, just write us an email if it's not clear.
Or that.
We can also send you the LT-SPICE files if you want, also no problem at all.
Yes. And also there's a next question from Mohammed. How can I order the EMI filter EVA board designed by you?
You can have my Altium files, no problem. I can also send you the Gerber files. Just write us an email.
Perfect. So we will get in contact with you afterwards. Nice. So let's hop on to the next question from Saliha. How to separate the CM noise and DM noise in a three-phase system from the measured noise without using probes?
Without using probes, it's getting difficult. So usually you can build your own current probe with, let's say, some kind of ferrite ring and put in some wires around it. But if you really would like to have a good measure, you need a calibrated current probe from Rode and Schwarz, for example, with an appropriate bandwidth of around 100 megahertz. And then you really can separate it. Otherwise, from a measurement point of view, it will be really difficult, to be honest. Because the listens cannot switch, they only switch between L1, L2, L3, and they do not provide you the possibility, the most listens, to measure all three channels at the same time. If you have a listen or you build your own listen where you can measure all the three RF channels at the same time, you can go or you can connect them to an oscilloscope and make the mathematical function. L1 minus L2 divided by 2 is the differential mode, and L1 plus L2 plus L3 is divided by 2 is the common mode, or divided by 3, sorry, it's the common mode. Exactly.
Thank you for the detailed answer. So let's have a look. There's a next one, also from Saliha. What methods can be used to analyze the saturation behavior of the common mode choke and how to deal with it?
Yeah, in some applications with a lot of leakage current, for example, if you have very long motor cables, for example 10 meter, even if it's shielded and you have a high DU to DT, There is a matter of, let's say, or there's a possibility the common mode current can be higher than a few hundred microamps. Then the possibility of saturation the core is very likely, because all these cores have no air gap, and even a few milliamps will saturate even bigger cores. You have to overcome this. That means you need a sinus filter at the output of the inverter, or you need cores with, let's say, fewer windings or nanocrystalline cores. They are, depending on the core, not so sensitive against this. And you can measure this current then also with a current clamp in the, let's say, overall phases. But this is something you should avoid really, otherwise the common mode shock will be getting very hot if you have high leakage currents from a common mode point of view. So better try to shunt back the current in the DC link directly. So if there's a possibility to place Y capacitors from the DC link to the motor output cables, the main portion of this common mode current is fed directly back to the source of interference, which is the 6-phase bridge MOSFET.
Good to know. Thank you very much. So let's see. There's a next question from Pedro. What's the best method to reduce the total volume of the filter, since same corner frequencies can be achieved with different C and L values?
After all, I'm a fan of multi-stage filters, because if you have seen, now we have big capacitors in a one-stage filter and a big inductor. If you split them into smaller components regarding the inductor and the capacitors, the high frequency behavior will be much more better, and you will overall save. Another possibility is to working with hybrid filters. So there is an active part which actively cancelling the common mode and differential mode currents, but most of them are only available for common mode, not for differential mode. So Texas, for example, provides such an IC, but it has also some limitations. Then you are binded, of course, to a two-stage structure, because this Texas EC, for example, is not working with a single-stage LC filter.
Perfect. Thank you very much.
Okay.
I think this one is building up on it. What are your considerations regarding multi-stage filter design?
What my
Considerations.
Considerations are, for example, you will find this consideration in the ANP015. So it's an app node related to a one-phase filter, but the idea behind and the calculations are pretty much working the same with three-phase filtering. So just download it, and I make a lot of comparison and measurements against it. So as I told you, I'm a fan of two-stage filters because the overall components by itself can be smaller and the high-frequency behavior can be better.
Thank you very much. So also Marius has an interesting question. For 115 VAC input delta configuration of X2 275, VAC capacitors for DM filtering would be favorable, sufficient, wouldn't it?
Theoretically, yes. But I'm always a fan of the at least 300 volt types 1 to have more margin. But of course, for the American voltage, the 275 volts, if you really only sell in this area, would be fine. For exception is, for example, the Canadian one. I think they have 580 volts, so therefore a much more higher voltage rating capacitors will be needed. But for Asia, like Japan and America, it's sufficient, right? You can save money and space.
Sounds perfect to me. So I have another one from Herbert. Is common mode or differential mode generally more difficult to filter?
The difficulty is the maybe changing standard in future as we go surely down, that our customers have to measure starting at 9 kilohertz, not with 150 like now. Both is challenging because if you really violate the limits in the lower frequency range, your filter components will be very, very big because the corner frequency has to stay even lower, at least 1 decay below. But generally speaking, as we can really identify and measure differential mode easier, then it's also easier to filter often than the common mode. And I would say common mode is more challenging in practice.
Perfect, thank you. So I saw that I skipped one earlier. What are your recommendations for selecting Resistors.
What my recommendation? So for one-phase application, you need at least a 14 millimeter disc with a high surge and 300 or 270 volt disc varistor. And for three-phase applications, where you usually have to apply 4 kV surge, a 20 millimeter disc varistor high surge type. So not a standard. I would also go for a high surge type. Because this kind of varistors, if they fail, it's not sure if they are open or if they are closed when they fail. And if your device is failing because of a defect varistor, because you underrated it too much, then it's very ugly in the end, or it's it's not satisfying. So I would say try not to save money at the varistor, because this component can really blow up the whole device and can give you some bad customer experience, I would say. So 20 millimeter disc for 400 volt applications.
Perfect. Sounds like you should pay attention to the quality.
Right.
I'm not sure if you already answered that one, because you were talking about the application note earlier. But Herbert asked, do you also have an application note for single-phase EMI filter design?
Yes, ANP 015 in German and in English.
Perfect, thank you very much. So there's one more question left. I think we are going to answer it. Can I find any information about saturation current for CM chokes in datasheets? Typical data concern on working DM current.
No. But if you have the request, send us the request and we can measure this for you for the part of interest.
Perfect. Thank you very much for your answer.
Welcome.
I think we are finished with our question and answer session. Oh, there just came one more question in. All right, here it is from Ingo. Lucky we still have time. Should I consider the capacitance of the MOV in the filter design? They are also placed across lines and to PE.
Okay. So if you place varistors against the lines to the protective earth, this is not so common, because many customers do not have so big coupling capacity from the lines to the protective earth that a big surge current can flow there. But if you place them, of course, you have to consider you have to place them in a series with a GDT or with thermo fuses, because if they fail, they can make a short to the protective earth. And yes, you can consider them also in the LT-SPICE simulation, for example. Just put them in as a normal capacitor with an ESL, which is, as you would say, roughly 10 or 20 nanohenry of ESL. ESR, I don't know really. But I think this is then a sufficient approximation, and they will have, of course, some influence in the COM mode behavior.
Perfect, thank you very much. I was just checking again to make sure that we didn't miss a question, but I think we are really done now. So thank you for the session, thank you for your presentation.
Welcome.
Thanks to all of you for your attention, and we hope to see you again in the next seminar.
Have a good evening.